Every day, the human heart beats approximately 100,000 times. In that 24-hour window, it processes 2,000 gallons of fluid, driving it through a vascular network that extends 100,000 kilometers. This quadri-chambered engine runs two parallel circuits simultaneously. The right side receives deoxygenated body blood, pumping it into the pulmonary circuit to the lungs. The left side receives oxygenated lung blood to ship to the body. A thick muscular septum keeps these flows separated. This compartmentalization allows the heart to process used and fresh blood at the exact same time without the two ever mixing. A single heartbeat lasts about 0.8 seconds. It begins with diastole, a relaxation phase where blood passively fills the upper atria. As blood enters the atria, the upper chambers contract. This atrial kick forces the final 20 to 30% of blood volume down through the open atrioventricular valves and into the ventricles. Once the lower ventricles hold roughly 130 milliliters of blood, they begin to squeeze. Since the valves are momentarily closed, the internal pressure spikes, a state called isovolumic contraction. These valves do not have muscles to pull them open or shut. Instead, they operate like mechanical doors that respond only to shifting pressure gradients. When the pressure inside the contracting ventricles overpowers the pressure in the atria, the fluid is pushed back against the entry valves. This force snaps these doors shut. This pressure-driven slamming of the valves creates the lub sound, the first half of a heartbeat. To eject the blood, the heart uses a helical ring. The muscle fibers are arranged in a spiral, allowing the heart to twist like a wet towel. This motion is what allows the organ to empty over 60% of its volume in a single squeeze. As pressure continues to climb, it eventually forces open the two exit doors, the pulmonary valve on the right and the aortic valve on the left. The two sides face very different resistances. The right ventricle only needs to push blood to the lungs at a low pressure of 25 millimeters of mercury. However, the left ventricle must generate 120 millimeters of mercury to drive blood past the aortic valve. This high pressure requirement explains the heart's anatomy. The left ventricle has a significantly thicker muscle wall than the right to handle the extra work. Think back to the pressure differences we just saw. When the heart finishes its squeeze and begins to relax, which specific valve must snap shut to prevent high-pressure blood from falling back into the heart? That is the aortic valve. The disparity in muscle thickness between the two chambers is a direct structural response to these differing physical resistances. As ventricles relax, internal pressure drops. Arterial blood tries rushing back, slamming exit valves shut to create the second heart sound, the dub. When viewed in real time, these phases, filling, the pressure spike, ejection, and reset, all occur within a 0.8-second window. The mechanics follow three rules. The right side moves blood from the body to the lungs. The left side moves blood from the lungs to the body. And the valves ensure a strictly one-way flow governed by pressure. By coordinating chamber orchestration, its helical geometry, and pressure-sensitive valves, the heart maintains the continuous delivery of oxygen and nutrients to the body's 75 trillion cells.